y double dash given by 1 minus 2y y dash. How do we get this? When you differentiate dy by dx, which is x minus y square, we differentiate the first term, that is x. Dx by dx is 1 minus d by dx of y square. So that is equal to 2y. But then we have got two variables, x and y. So they are not complete derivatives, and hence we have to differentiate y with respect to x again, because y is a variable here. So we'll have 2y dy by dx. So y double dash, that is the second order derivative that we get, is 1 minus 2y y dash. Similarly, differentiating the second order derivative further with respect to x, we have y third order derivative, which is given by minus 2y y second order derivative minus 2 first order derivative of y square. The fourth order derivative is given by further differentiating the third order derivative with reference to x, which is now given by minus 2y third order derivative of y minus 6y double dash y dash. And y fifth order derivative, which is obtained by differentiating the fourth order derivative with reference to x, is given by minus 2y 4 dash minus 8y dash y triple dash minus 6y double dash whole square. You must be aware of the differentiation, and hence I will not delve into the differentiation in detail. Let us now take an example. We have been given that y of 0 is equal to 1. That is, at x equal to 0, y is equal to 1. Since it is an initial value problem, x and y are the first points or the starting points, and we shall denote them by x1 and y1. Hence, we can say that x1 at x1 equal to 0, y1 is equal to 1. Now, if we compute the derivatives or the value of the derivatives, we have, from the equations that we just obtained, we have y dash is equal to minus 1. That is, by simply substituting the value of x equal to 0 and y equal to 1 in the derivative equations, we shall have the values. First order derivative y dash is equal to minus 1. Second order derivative equal to 3. Third order derivative equal to minus 8. Fourth order derivative equal to 34. And fifth order derivative equal to minus 186. Now the Taylor series expansion is thus for this equation y of x, because we now need to find out the value of y at x equal to 0.1. So let us first put in the generic equation. That is, the Taylor series expansion now is y of x is equal to y1. Earlier we had written y of x1. Y of x1 is nothing but y1. So y of x is equal to y1 plus x minus x1 into y dash 1, that is the first order derivative at x equal to 0, plus x minus x1 square upon 2 factorial into second order derivative y1, plus x minus x1 cube upon 3 factorial into third order derivative at y1, plus x minus x1 raised to 4 upon 4 factorial into fourth order derivative of y1, plus x minus x1 raised to 5 upon 5 factorial into fifth order derivative at y1. Let us substitute the values that we had obtained earlier for all the derivatives. Now y of 0.1 is equal to 1, which was our y dash, which is our y1. So 1 plus, what is the value of x? The value of x is 0.1, because this is the value of x at which we need to find out the solution of the ordinary differential equation. So we substitute 0.1 in place of x and 0 in place of x1 and the values of the derivatives that we had obtained. After substitution and subsequent solving, we get y of 0.1 is equal to 0.9138. I have put down the intermediate values for you so that you know how the calculation takes place. The values of each of the terms have been put down. Thus, When we use Taylor series method in order to find out the solution of ordinary differential equations, we need to compute the values of the different order derivatives from first to n. Substitute these values into the Taylor series equation and find the solution on further computation. The second one-step method that we would be talking about today is the Eulers method. This is the simplest form of method and most popularly used method in order to find the solution of ordinary differential equation. Now, Eulers method uses the mean value theorem. I hope you must be aware of this particular theorem. However, let us revise what the mean value theorem is. If a function is continuous and differentiable between 2 points, say x1, y1 and x2, y2, where x1, y1 is the initial point and x2, y2 is the subsequent point, then the slope of the line joining these points, that is x1, y1 and x2, y2, is equal to the derivative of the function at least at one other point, say C, between these 2 points. So if we connect 2 points x1, y1 and x2, y2 by a straight line, the slope of this line is equal to the derivative of the function at any other point on this line. This is the mean value theorem. Now we shall use this theorem in order to derive our Eulers method. That is, if I have got these 2 points x1, y1 and x2, y2, the first order derivative at a point C on the line connecting the 2 points is given by y2 minus y1 divided by x2 minus x1. Let us substitute x1 in place of C and x2 minus x1 shall be replaced by h. Now what is h? H is the difference between two consecutive xi's. Here we shall be computing because xi's are our independent variables. Now we shall be computing the solution at a given xi. In order to compute the solution at a given xi, since we are using the one-step method approach, we shall be using one preceding value. That is the previous value of the function or of the ordinary differential equation at x equal to xi minus 1. Now here the difference between the two xi's, that is xi and xi plus 1, is called h, and the difference between the consecutive xi's would always remain same. In other words, the xi's that we would be using are equidistant from each other. That is, they would be having an equal interval size of h. So let us substitute x1 in place of C and h in place of x2 minus x1. Then what do we have? We get y dash x1, that is the first order derivative of the equation y at x1 is now given by y2 minus y1 upon h. Now simply on rearranging these terms, we get y2 minus y1 is equal to h into y dash x1. Now further rearranging would give us y2 minus y1 is equal to h into, what is y dash x1? Is nothing but the value of y dash that is given to us. What is y dash x? Y dash x is equal to f of xy. That is the ordinary differential equation. So we would now replace y dash x1, this is at x equal to x1, by the function f of x1 y1. And on rearranging, we have y2, that is simply taking y1 on the right hand side of the equation. We get y2 is equal to y1 plus h into f of x1 y1. That is the value of the function at the initial point x1 y1, which is given to us. Similarly, y3 is equal to y2 plus h into f of x2 y2. And in general, we can say that yi plus 1 is equal to yi plus h into f of xi yi. Since this is a one-step method approach, in order to compute yi plus 1, we only need one preceding value of yi and the first order derivative at xi yi, which is given by f of xi yi. Let us take an example in order to understand how to solve using Eulers method. Solve the following ordinary differential equation, that is dy by dx is equal to 3x plus y. This is the equation that has been given to us. We are now supposed to solve this ordinary differential equation using Eulers method, given the initial value that at x equal to 0, y is also equal to 0. And this values or the solution is to be computed in the interval 0.1 and 0.5. That is for x that belongs in the interval 0.1 to 0.5. And the step size, if you remember, I just mentioned that these xi's are equidistant. So what is the step size? The step size that we are supposed to take here is 0.1. So now, using Euler's method, the generic formula is yi plus 1 is equal to yi plus h into f of xi yi. At the initial point, yi and xi, that is x1 and y1 are given to us. So y2 can be computed as y1 plus h into x1 y1. So let us substitute the values. The value of x is equal to 0 and the value of y is equal to 0 at the initial point, that is y1 is equal to 0 at x1 equal to 0, and h is given to us as 0.1. Now y2 is equal to, let us substitute the value of y1, which is 0, value of h 0.1, f of x1 is 0 and y1 0. What is the form of fxy? 3x plus y. So if we substitute the value 0, 0 into the equation, we get 0. 0 multiplied by 0.1 is 0, added to 0 is 0. Hence the value of y2 is equal to 0. Now we have two values. y1 is equal to 0 at x1 equal to 0. y2 is equal to 0 at x2 equal to 0.1. Similarly, we can continue computing y3 as y2 plus h into f of x2 y2. y4 is equal to y3 plus h into f of x3 y3, and so on. And we can then place the values in a tabular form. So for this particular equation or this particular example, we saw that at x equal to x1, y was equal to y1, that was 0, 0, which was the initial point that was given to us. At x equal to 0.1, we computed the value of y2 as 0. Subsequently, using the preceding values, in order to compute y3, we just use the values of x2, y2. In order to compute the value of y4, we use the values computed at x3, y3. Now from this we can see that we have used one preceding value in order to find out the value of the succeeding points. This is the Eulers method. Another category of methods in one-step methods are RungeKutta methods. In RungeKutta methods, we would be talking about second order RungeKutta method and fourth order RungeKutta method. Let us have a look at RungeKutta second order method. Given the following differential equation with an initial condition y equal to y1 at x equal to x1, every time you would observe that I keep on saying with an initial condition y is equal to y1 at x equal to x1. Why? Because we are dealing with initial value problems. The differential equation that has been given to us is dy by dx is equal to f of xy. At the initial point, now in RungeKutta second order method, how do we solve it? At the initial point, that is x1, y1, we would compute the slope of the curve as f of x1, y1. And we shall call it S1. That is the first slope, that is S1. Now at the next consecutive point, again we shall compute the slope of the curve. Now the next point is x2, because we said we start with x1, subsequently x2, x3, x4 and so on. At the next point x2, y1 plus s1h, we shall compute the slope as f of x2 y1 plus s1h, because f of xy is dy by dx, dy by dx is the derivative, and the derivative is the slope, and hence for the first initial point x1 y1, f of x1 y1 is called the slope of the curve at point x1 y1, and we call it s1. Similarly, at the next point x2, y2 is equal to y1 plus s1h, that is using the previous slope, and the slope at this point shall be computed as f x2 y1 plus s1h. Here we shall call this slope as s2, and x2 is nothing but x1 plus h, because we said they are equidistant point, the step size is h, and hence x2 is equal to x1 plus h. Once we have found both these slopes, now why two slopes? Because this is a second order method. Second order methods means for the same line we are finding out two slopes, one at point x1 y1 and another at point x2 y2. Now for a particular line connecting 2 points, the slope has to be equal at any of the points on the line. But since we are computing two slopes, the final slope of this particular line connecting the 2 points shall be considered as the average of the two slopes s1 and s2, and we shall call it s. Hence s is given by or is got by s1 plus s2 the sum divided by 2. So we find out the average of the two slopes. Now the value of the dependent variable y is given by y2 is equal to y1 plus hs. So the next value of y is computed by adding h into s, that is the step size, and the slope, the average slope, to y1, that is the preceding value. By doing so, we shall be getting the subsequent value of yi, where s1 is equal to f of x1 y1, s2 is equal to f of x1 plus h, y1 plus s1 into h, and s is the average of s1 and s2 given by s1 plus s2 upon 2. So in general, we can say that s is obtained by si plus 1 by 2, and si is equal to f of xi yi, and si plus 1 is equal to f of xi plus h.